Hello, this is Christina Long, and this is the Science 411. Today's live session is going to be covering physical and chemical changes and then phase changes. It's not too tough, but it's something that's worth going over. So welcome back. I hope you're enjoying your time at home. And let's go ahead and get started here. So for chemical and physical changes, there's a couple of things that you need to know. For chemical changes, the main thing that you need to understand is that the substance changes chemically, and as silly as that sounds, it's truly the essence of what's going on. So when you look at the substance sodium chloride, when sodium chloride in itself is table salt. It's what you put on your French fries or your mashed potatoes or whatever it is you use. And when it goes through a decomposition reaction, it's going to break down into sodium and diatomic chlorine. Now, sodium and diatomic chlorine, sodium is an explosive metal, and diatomic chlorine as a poisonous gas. So obviously, those two by themselves, strangely enough, they can't come together and make a compound unless they chemically change. So you've got an explosive metal, you've got poisonous gas, and switcho-changeo through the magic of chemistry. Now you've got table salt, which I'm pretty addicted to. So when you're looking at a chemical change, it truly is just a change. Hi, Israel. So another thing to remember when you're dealing with this is that you can't get it back. You can't get your original substance back unless you go through another chemical change. So for chemical changes, again, the actual formula is going to change. It's not about what it looks like, it's what the actual formula is. So when you're here, you've got your sodium chloride and it breaks down. So unless you run another chemical change to get that back, you're not going to be able to. Another example of a chemical change would be like burning something. If I were to take, a piece of paper, and I've got whatever chemical compound that paper is, and then I light it on fire. Well, I know from combustion reactions that as long as I've got oxygen and I have a fuel, which is that piece of paper, then it's going to turn into CO2 and water. And again, it's a chemical change. I can't get the original piece of paper back. Now I've got ash and some other things, but I can't get it back. Now, chemical changes are, they're a little bit easier to come by and actually are a little easier to identify because there are not that many of them when we're talking about schoolwork type of stuff. Most changes you're going to see are going to be physical changes. Now, physical changes are going to be really just the physical state is going to change, but the chemical compound itself is going to stay the same. They're mainly phase changes. So if you look at the example here, you've got water, which with that little S there at the bottom, that's telling you that it's a solid. And then it melts, essentially, and it goes to water, which is a liquid. Well, it's still water. It's still dihydrogen monoxide. It just looks different. So you've gone from a solid to a liquid, which means that you're going to be dealing with a phase change, which is just a physical change because you're still dealing with water. Okay? So now, when you're looking at different types of changing, there are some examples that you can take a look at. So water boiling into steam. Water boiling is going to be a physical change. And ice cream melting. It's melting, it's a phase change, so that's going to be physical as well. Then a bicycle rusting in the rain. So anytime you see the term rust, rust is definitely a chemical change. So essentially, if you're talking about a bicycle rusting in the rain, you're talking about iron in that bike, and then it reacts with diatomic oxygen in the air, and then it's going to make Fe2O3, which is iron 3 oxide, which is definitely not the same as the iron. Okay, so rusting is always going to be a chemical change. Now here's an interesting example. What if you took a banana turning brown? So when a banana turns brown, there's actually a chemical change going on, because the chemicals inside there they're aging and they're changing into other things. So the brown banana actually tells you that it's more ripe, and that's great and all, but it's chemically changed. Now if I took a knife and sliced up that banana, that's a physical change. Just because it's in smaller pieces doesn't change the fact of that it's a banana. A ripened banana is chemically different than an unripe banana. Tearing a piece of paper into pieces, it's still paper. It doesn't matter what shape it's in, therefore it's going to be a physical change. Candle wick burning. You got your clue there, burning. It's a combustion. Can you get the candle wick back? No, you can't. So when you've got burning, any type of combustion, that's going to mean that you're dealing with a chemical change. Water freezing into ice. Freezing is telling you it's a phase change, which in turn tells you that it's a physical change. A carton of milk going sour. Well, any kind of food that's going sour, going bad, or spoiling, basically it's happening because there's bacteria in there, and it's chemically changing the substance. And when it's chemically changing the substance, it's a chemical change. A loaf of bread cut into slices. It's still bread. It's just not in a big loaf. It's in little slices. It's the same thing, so it's a physical change. And then burning toast in the toaster. Burning, associated with combustion. All of you, I think, have had burnt toast, or maybe you've overcooked pizza and the crust is burned on the bottom. It doesn't taste the same. And the reason it doesn't taste the same is because it's got a whole lot of burnt carbon in there. And it's because it tastes different because it is different and it's chemically changed. So when you're looking at chemical and physical changes, you're going to be looking at chemical changes. Did the substance chemically change? Can I get the original substance back? If you can't, it's a chemical change. If it changes phases, if it goes from a solid to a liquid, does that mean that it's chemically different? No. It just means that it changed phases. That's a big thing. Physical changes is not going to change that chemical formula. If you started out with H2O and you end with H2O, no matter what it looks like, it's still going to be a physical change. All right. Now phase changes. Phase changes, there's a diagram that you really, really, really need to know. And it's going to look a little bit like this. And hopefully you've seen it before, but it's very important that you understand what's going on within this phase change diagram. And that's exactly what this is a phase change diagram. And there are a few things that are going to come into play here. And when I say it's a phase change diagram, then the only type of change that we're dealing with here are just physical changes. So I'm going to start writing some things in red and some things in blue, and we'll explain why here in just a minute. But for this case, we're dealing with water, and I'm going to throw some temperatures here. You've got 0 degrees Celsius, and then you've got 100 degrees Celsius, and hopefully you're already kind of ahead of me in knowing where I'm going with this. If I'm dealing with 100 degrees Celsius, then I'm going to go ahead and say, okay, I'm dealing with boiling, evaporation, and vaporization. And then on the 0 side, the 0 degree side, then what I'm dealing with is freezing. No, I'm not going to be dealing with freezing. I'm going to be dealing with melting. Now, The reason I did these in red is that these are endothermic reactions or endothermic processes. And that's because when you add heat to the system, they're going to get warmer, and it's going to cause the process to move from left to right. So as you add heat, you're going to go from a solid to a liquid up to a gas if you continue to add the heat. Now, the opposites of these, which strangely enough happen at the same temperature. So if for boiling, vaporization, and evaporation, the flip side of that is condensation. And the flip side of melting is freezing. So why do I include the blue? Well, I'm including the blue there because it's exothermic. And it's an exothermic process. And what happens is it loses heat. It's going to release heat, and it's going to release it into its surroundings, and the molecules are going to get closer and closer and closer together the more heat you pull away. And those are exothermic processes. Now, those, instead of going left to right, they're going to go right to left. Now, there are two other processes that I need to add. Some of you are going to have teachers that are going to want you to know what these are, and some aren't. But if you're going from a solid to a gas, and in some cases this will happen, it'll skip the liquid phase, and in that case, this is something called sublimation. And for some of you, this is a new term. And it's basically a very endothermic process where it skips that liquid phase. Now, I think all of you have probably seen an example of this, and that's with dry ice. If you remember, if you've ever been to a Halloween party or anything like that, or sometimes like middle school dances, they'll have dry ice. And the dry ice will be there. You add a little water to it, and boom, it then starts to create this fog. And so it's going from a solid directly to a gas and skipping that liquid phase. And that's called sublimation. Now, the opposite of that is called deposition. And the way I remember this is the gas is going to leave a deposit as a solid. And that's where a gas is going to go. It's going to skip that liquid phase again, and it's going to go straight from a gas to a solid. Now, there are a few things with this. You've got molecular motion of solid, liquids, and gases, and you have to kind of think of those. A solid is going to have a very little motion, and it does move a little bit. It's called Brownian movement, but it moves and vibrates at a very small rate. And then as you add heat to it, it starts moving more and more, and then it gets wider and wider apart. And then as you get more heat, it's going to expand out to a liquid, and it's going to have more movement. And at that point, you're going to be able to pour things, and the molecules are going to slide back and forth across each other. And then when you add even more heat, then you've got the molecules that are bouncing all around as a gas, and those have the highest energy. Again, that's all endothermic. As you're adding energy to it, it gains more and more motion. They begin to spread out, and they have a lot more energy. Conversely, though, when you're dealing with an exothermic reaction, as you take energy away in the form of heat, when you start pulling that away, those molecules get closer and closer and closer together, and they have less and less movement. Now, when you're looking at the phase change diagram, the mistake that most people make is they want to put solid, liquid, and gas on that flat line, and that's not where you put it. Instead, you need to put your solid, liquid, and gas on the slopes. Why? Well, because let's just take, for example, water. Water can be a liquid basically between 0 and 100 degrees Celsius, anywhere in between there. There's that range. Ice is not just ice at just 0 degrees Celsius, but it can get as cold as you can make it. In the classroom, for our classroom, We get it down to about -20, and then we start breaking thermometers, and we got to stop. Steam gets hotter than 100 degrees Celsius. So those happen in a range. But the question becomes, why does the phase change, why is that flatline? Why would it do that? Because it definitely does. So in these cases right here, that temperature remains the same the whole way through the phase change, and that temperature is not going to change or drop until that phase change is done. So let's talk a little bit about that. And I'm going to use the example of freezing water. So if I have some water, I'm going to look at the molecules, and excuse my little cartoon drawing. For those of you that know me, you know that I am not an artist or pretend to be one. If that's a liquid, and I'm going to go to my cartoon drawing of a solid, notice that there are a few changes here. Number one, the molecules are fairly tightly packed. They're somewhat ordered. They don't seemingly have a lot of movement. Now, liquid molecules can move around a little bit because all of you can pour your water or your Coke or whatever it is. You can pour that. But when you get to, not a gas, goodness, when you get to your solid, you're not able to do that. And so I'm looking at the freezing process here. And in order to do that, in order to freeze a liquid, let's say that I'm starting right here on my diagram. And let's say that that's 50 degrees Celsius. And I take a sample of water that's 50 degrees Celsius, and I put it in a surrounding of ice, somewhere that's really cold. What's going to happen to that sample of water is it's going to lose temperature. It's going to go drop, 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 drop down. It's going to lose heat. Now, where does it lose it to? It loses it to the surroundings. And it's giving it away. It doesn't need it. It's cooling, cooling, cooling. It's an exothermic process, okay? And so it's going to release the heat. But then what we found in lab, and it's kind of fun to do, but if you're taking the temperature of that sample of water, what's going to happen is, let's say that it's dropping, 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 and it gets to 0 degrees. Now what happens at 0 degrees? Well, it freezes. So at 0 degrees, it's going to freeze. And what you're going to find is, if you were to take the temperature of it every minute, it's going to stay at 0 every minute for about 4 to 5 minutes. Now, you haven't taken it out of the cold area. You haven't done anything different. The water's gotten colder, 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 and then it flatlines for 3, 4, 5 minutes. And most people, especially in class, say, wait, my lab is broken, something's wrong. No, nothing's broken. It's staying at 0, stable, 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 and then, like magic, the temperature begins to drop again. And then that's when you got to the -20 and you break a thermometer, and it's fun. But why does it flatline at 0? The reason it flatlines at 0 is because what's happening here in this process, as the liquid is dropping, it's releasing heat. And that's great up until you get to the 0. It's still getting colder, but what's happening? Does your room clean yourself? Does it clean itself? Mine does not. My house, I have realized that my house does not clean itself while I've been home. The law of thermodynamics says that over time, a system is going to become more disordered. And I have found that in my own house, unless you add energy to it. So every time I see you, I always say, make good choices and clean your room. All right, so I want you to clean your room. Do you have to clean it every day? Well, it could be nice if you did. Now, if you add energy to your room to clean it every day, it's going to stay ordered. If you don't, you wait until the end of the week. By the time you get to the end of the week, it's kind of a mess, and it takes more energy to do so. These molecules, just like your room, these molecules do not order themselves. Your room does not clean itself. These molecules do not order themselves unless outside energy is added. So, when the temperature drops, and drops, it's getting rid of all that energy. But then it flatlines. What's happening? That energy is being used to create bonds and order. So those molecules are not going to arrange themselves without outside energy. And so the reason that that temperature drops or it flatlines is that that energy, in the case of freezing, instead of it being released, it's being used to order the molecules. You know that the freezing process is done once the temperature begins to drop again. So at that point, all your molecules have changed from a liquid to a solid, and then it's able to drop. That happens in every single phase change situation. So when the temperature flatlines, you know that you're in the middle of a phase change. Now, if it's an exothermic reaction, or exothermic process rather, you're dealing with condensation or freezing, then the molecules are being used to order or add order to the molecules to bring them closer together and add more order to the system. Conversely, though, if it's an endothermic system, then you're going to raise the energy, raise the temperature, and then when it flatlines, instead of it creating order, instead it's going to create disorder in the system, and it's going to break those bonds to allow them more movement. So, in looking at your phase changes, you've got quite a few. You've got boiling, evaporation, and vaporization. And that's going to be going from a liquid to a gas. And then when you go from a liquid or a solid to a liquid, that's going to be dealing with melting. Those are all endothermic. And then don't forget sublimation, which is going to go from a solid to a gas. And then from the back end, or the opposite side, is going to be your exothermic, and that's going to be your condensation, your freezing, and your deposition, and those are going to lose energy. Some things to remember. Going to be your states of matter are going to be on the slants, and your phase changes are going to be on the flat side. And pretty much that's about all we have, unless any of you have some questions. But in general, the things that you need to know for this section for me is going to be the difference between a physical and a chemical change, and then your phases of matter. And that heating curve of water, that phase change diagram, is a huge part of what I'm asking you to know. So again, thanks for joining me today. And if you have any questions or comments, please make sure to include it. Make sure to comment if you have any questions, and make sure to subscribe to the Science 411 and click on the bell so you can get notifications. And I hope you guys have a great day. Thanks for joining me. Bye.